In this lecture, we will cover section 1 of chapter 10, which is on inference for a quantitative variable. We'll start by looking at confidence intervals. We'll talk about inference problems for means and how they are different from inference problems for proportions. We'll talk about what to do when the population standard deviation is known or when it's unknown. We'll talk about how to construct confidence intervals for the mean when the standard deviation is known. We'll check for normality, and we'll look at some details of the confidence interval for the mean. We'll also talk about hypothesis tests for a quantitative variable. We'll talk about the 4 steps in conducting a z-test for a population mean. We'll look at examples using one-sided and two-sided alternatives. We'll relate the hypothesis test back to what we talked about confidence intervals. We'll talk about the factors that go into rejecting the null hypothesis. And we'll talk about inference using the t-distribution versus the z-distribution. Much more about that later. To review, in the 4 stages of statistics, we are in statistical inference, and we're talking about inference for one quantitative variable. We'll start by talking about the relationship between inference problems for proportions and inference problems for means. Let's look at how they're the same. First, just as before, we'll have 3 different ways that we can ask a question about inference. We can make a point estimate, we can construct a confidence interval, and we can perform a hypothesis test. Additionally, before we do any inference, we'll want to make sure that the point estimate is an unbiased estimator. There's some things that we have to check for both proportions and means. Confidence intervals are constructed in much the same way. The center of the interval will be the point estimate, and we will add and subtract a margin of error. In general, that means we're going to take the sample statistic. For means, that's going to be the mean of the sample. For proportions, it was the proportion in the sample. And we'll add and subtract some multiplier times the standard deviation of the sample statistic. In order for this to work, the sample statistic must be unbiased. We don't want to push the confidence interval one direction or the other. The sample must be large enough so that the multiplier is correct. In other words, we want to make sure that using the normal distribution, for example, is appropriate. Remember that the higher our confidence level, the larger this multiplier is, which makes our interval wider. Also, in order to use the standard deviation of the sample statistic as an estimate for the population, we need to make sure the population is at least 10 times the sample. As before, a larger sample means a smaller standard deviation, which leads to a narrower interval. Also, we can interpret the interval in the same way as we interpreted the confidence interval for proportions. And the confidence interval for means is related to the hypothesis test in exactly the same way as it was for proportions. For the hypothesis test, our question is the parameter, which we don't know, equal to some proposed value? There are 3 ways that we can formulate the alternative, as before, using a greater than, a less than, or not equal to. There are 4 steps that we will follow that follow the 4 processes of statistics. First is data production. We want to make sure the sample is unbiased. We want to make sure the sample is large enough and the population is large enough. Next, we will find the sample statistic and standardize it and ask, is it large? We'll measure how large the sample statistic is based on its standardized value, just as we did for proportions. Next, we'll find the p-value, which is the probability of getting a sample statistic as weird or weirder than our sample. In other words, we want to know if the p-value is small. We'll use the same criteria for smallness of a p-value as we did before. And finally, we'll do our inference. We will reject the null hypothesis if that p-value is small. As before, the p-value for a 2-sided alternative is 2 times as big as the p-value for a 1-sided alternative. We will call the cutoff level alpha, as before. We will typically use 0.05. Unless you see otherwise, you can make that assumption. That alpha is the probability of making a type 1 error. We'll reject the null hypothesis if the sample statistic is far away from the proposed parameter, that is the parameter value that we assume in the null hypothesis. We'll also reject the null hypothesis if n is large or if the standard deviation is small. A type 2 error, that's a false negative, is also possible, especially when we have a small sample size. All of this relates directly back to what we did for proportions. It's all exactly the same. Now, how are they different? Well, first, proportions are the way that we summarize categorical variables, and means are the way that we summarize quantitative variables. We summarize quantitative variables using the mean, the sample mean, the population standard deviation, and the sample standard deviation. For proportions, remember, we got the standard deviation directly from n and p. We didn't need all this extra information. The biggest difference you'll find is that when we standardize, we're not always going to call it z, because we can't always assume that it will follow the normal distribution. There's no easy way to give a rule of thumb for how big n has to be to get normality. To know how big n needs to be, we have to look at the shape of the sample data, as we did before. The more normal the sample looks, the smaller n needs to be. The more skewed the sample looks, the bigger n has to be. Now, as before, there are three types of inference problems we can talk about. For example, we can talk about the mean yearly earnings for a sample of 446 students at a particular university was $3,776. What can we infer about the population? Well, we might just simply make our best guess for what the mean earnings would be for all students. We might ask what interval should contain the mean earnings for all students. And finally, we could ask if we have convincing evidence that the mean of earnings for all students is less than $5,000. Question number 1 is asking about a point estimate. Question number 2 is asking for a confidence interval. And question number 3 is asking for a hypothesis test. Let's start by looking at point estimates. Remember, the sample mean is a random variable. The mean of the sample means should be the same as the mean for the population. That means that the sample mean x bar is an unbiased estimator for the population standard deviation. The sample has to be random in order for that to be true. So, suppose we have an anonymous online survey of introductory statistics students with various ages and various majors at a university. From that, we get sample mean earnings. Is this sample representative? Well, do you think the values of the variable were recorded without any bias? I think that as long as there are various ages and various majors represented in the sample, then this sample would be representative for that university. But that's the only population we'll be able to draw any inferences about. Because socioeconomic conditions depend on the school, that's what keeps us from generalizing to other universities. We don't know if our sampling frame is appropriate. Because the survey is anonymous and online, we wouldn't expect biased responses. Now, back to our example about our representative sample with mean earnings $3,776. Based on this sample, what is our best guess for the average earnings for all students at that university? Well, based on the data, our best guess would be $3,776 because sample mean is an unbiased estimator. Notice that to do a point estimate, we don't need the standard deviation. because this isn't reliant upon the spread of the data. It only focuses on the center. For the other types of inference, we will definitely need some measure of spread to indicate, for confidence intervals, how wide the interval is going to be, and for hypothesis tests, in order to compute a probability. So let's turn our attention to confidence intervals. When the population standard deviation is known, when we standardize sample mean, we'll call it Z. When the population standard deviation is unknown, we'll call the standardized x value, x mean, T. So if the standard deviation of the population is known, we'll use Z, and we'll use the normal distribution. Remember, the letter Z indicates normal distribution. If the population standard deviation is unknown, we will call the sample mean T. In practice, if n is really big, the distinction between Z and T is so small that it won't make any difference. Since we'll have technology at our disposal, we'll always use T if the standard deviation of the population is unknown. This histogram gives you a sense of the difference between Z and T. Notice that the tails of T are fatter. That makes our confidence intervals wider, and it makes our hypothesis tests result in larger p-values. That makes it harder to reject the null hypothesis. We will talk about the t distribution after we talk about doing inference with Z. To review, if we have a random sample with n individuals sampled, the population has mean mu, and the standard deviation is sigma in the population. The sample mean, x bar, will be centered at mu. The standard deviation for x bar will be the population standard deviation divided by the square root of n. And as long as n is big enough, the shape is approximately normal. Now, because that shape is normal, we can use the normal distribution. In particular, we know that there's a 95% chance that the sample mean is within 2 standard deviations for the sample mean of the population mean. This gives us our confidence interval. So a 95% confidence interval for population mean is sample mean plus or minus 2 standard deviations. Again, this is standard deviations for sample means. The sample must be unbiased in order for x bar to be an accurate guess for mu. The population size has to be at least 10 times the sample size in order for the sample selection process to be approximately independent. And n has to be big enough to justify using the 2. That is, n has to be large enough for this, the sample means to be distributed normally. Let's take a look at a few guidelines for when the sample mean will be approximately normal. We've seen these before. If the sample data looks normal, we can assume that x bar will be normal. If the sample data seem to be fairly symmetric and n is at least 15, or if the sample data seem to be moderately skewed and n is at least 30, or if the sample data is very skewed and n is much larger than 30. It might also pay off to consider what you think the sample data would look like, in addition to creating a histogram. Back to our original question. In our sample, the mean yearly earnings was $3,776. Let's assume for now that the population standard deviation is $6,500. Assuming our sample is representative, what would be our confidence interval? The 95% confidence interval is the sample mean plus or minus 2 standard deviations for sample mean. That is 3,776 plus or minus 2 times 6,500 divided by the square root of the sample size, 446. That's approximately $616 when we do that computation after the plus or minus, which gives us an interval from $3,160 to $4,392. Because the data here, if you recall, we've seen this histogram before. The histogram is very right skewed, but 446 is a very big sample. It's okay to use the normal distribution for this. Now, how do we interpret that confidence interval? Can we say that $5,000 is a plausible value for population mean earnings? Well, $5,000 is not in our confidence interval, so no. This is related to what we're going to do later on with hypothesis tests. Let's look at how sample size affects our confidence interval. Remember that for our yearly earnings, our 95% confidence interval was $3,776 plus or minus 616. What would happen to the confidence interval if we reduce n by a factor of 4? Say we reduce it to 111 instead of 446. Dividing n by 4 multiplies the width by 2, because if we divide that square root of n in the denominator, if we divide the n under the square root in the denominator by 4, that, as a result, multiplies by the square root of 4, which is 2. So that will double our width. For other confidence levels besides 95%, remember our 95% confidence interval is this. What would we do for, let's say, a 90% or 99% confidence interval? Just like for proportions, we'll use different multipliers. The ones that we would use for 90% and 99% are 1.645 and 2.576 respectively. Remember, we can find those numbers using inverse norm on our calculators. Next, I'll show you how to use your calculator to compute these confidence intervals. Confidence intervals are located in the Tests submenu of the Statistics menu. We're constructing confidence intervals using Z, so we'll select Z interval. The first thing that you are asked is whether you want to input data or statistics. You'll use data if you have actually your raw sample data. If you select data, notice you'll see a place to tell the calculator where the data is, L1 by default. But for us, we're given statistics in this example. We're given 6,500 for the sample, for the population standard deviation. We're given $3,776 for the sample mean and 446 for the sample size. The next thing I can enter is the confidence level. So I can use 0.9, 0.95, 0.8, anything I want. Let's do the 90% confidence interval, and we'll calculate. And our interval gets reported. It's just that easy. This chart also shows you what the appropriate multipliers are. For a 98% confidence interval, we'll use a multiplier of 2.326. So to review, we can use this chart to figure out the appropriate multiplier for our confidence intervals. To be more precise than 2, a 95% confidence interval would use a multiplier of 1.96. We'll typically round that off to 2. So with our same situation, let's compute 90% and 99% confidence intervals. Confidence intervals, remember, are the sample mean plus or minus some multiplier times the population standard deviation divided by the square root of the sample size. So, to construct the 90% confidence interval, we'll use a multiplier of 1.645, which gives us an interval of approximately $3,270 to $4,282. For the 99% confidence interval, we'll use a multiplier of 2.576, which gives us a confidence interval of $2,983 to $4,569. Notice that to get the higher level of confidence, we got a wider, less precise interval. Here's what this looks like in practice. For a 90% confidence interval, if we take many samples over and over and over again and construct confidence intervals, 90% of them, which works out to 18 out of 20, should contain the true population parameter. If we widen the intervals to 95% intervals, then 19 out of every 20 would contain the population parameter. Here's what that looks like in practice. What we're about to do is simulate choosing a bunch of different intervals, a bunch of different samples, 20 of them in fact, and we will construct the corresponding confidence intervals, and we'll see how we do at capturing mu inside the interval. Let's start with 90% confidence intervals. Notice the centers of these intervals are all a little bit different because the means of our samples will all be a little bit different. Sometimes they'll be bigger than mu, sometimes they'll be smaller than mu, but we'd expect them to be pretty close. If we continue constructing our 90% confidence intervals, we will expect 2 out of the 20, on average, to miss. Sure enough, that's what we saw here in our simulation. Now, if we switch to 95% confidence intervals, we'll expect these intervals to be a little bit wider because we'll be more confident. So if we go back to the samples and widen them out to match a 95% confidence level, these are represented with the blue bars. Notice that one of our 90% confidence intervals that missed the mark before now captures the mean. Our other one didn't. So in practice, 19 out of every 20, or 95%, of the 95% confidence intervals we construct should capture the mean. So that leads us to the way that we interpret confidence intervals. So for, like, say, a 95% confidence interval, we'll say we are 95% confident that the interval contains the unknown parameter. Or we could say that 95% confidence interval's long-run probability of capturing the unknown parameter is 95%. So if we construct a 95% confidence interval for mean U.S. household size, we get 2.166 to 2.714. Which of the following are true? The probability is 95% that mu is in that interval? No. When we talk about probability, we talk about something that's random. Mu is fixed. It's not a random variable. The probability that mu is in that interval is either 0 or 1 because it either is or it isn't in there. So this is false. 95% of household sizes are in the interval from 2.166 to 2.714. Here we're talking about household sizes. This confidence interval is a confidence interval for mean household size. This is false. The probability is 95% that x bar, our sample mean, is in that interval. No. When we're talking about confidence intervals, we're talking about confidence that mu is in the interval, not x bar. X bar has to be in the interval. Remember, x bar is the center of the interval. So this one's false. We are 95% confident that x bar is in that interval. Well, again, we're talking about x bar. These confidence intervals are for mu. This is false. Remember, x bar has to be in the confidence interval. It's the center. We are 95% confident that mu is in that interval. Yes, that's exactly our interpretation. The probability is 95% that our sample produces an interval which contains mu. Yes, this is the other way we can interpret our confidence intervals. Only these last two are correctly stated. So again, looking at our mean for yearly earnings, we looked at a point estimate. That's our best guess for the mean earnings of the population. We looked at a confidence interval. That's the interval that should contain the mean earnings for all students. Next, we'll turn our attention to whether or not we have convincing evidence that mean earnings for all students is less than $5,000. This is the hypothesis test. Again, remember that our sample mean should be is a random variable. It's centered at mu. The standard deviation is the population standard deviation divided by the square root of the sample size. And the shape is approximately normal as long as n is big enough. As long as the population standard deviation is known, our standardized mean will follow the z, or normal, distribution. So here's how we do the hypothesis test. We'll start by stating two hypotheses, as before, a null hypothesis and an alternate hypothesis. The alternate hypothesis will be stated using inequalities. We'll start by considering the sampling and the study design. Then we'll summarize using the mean for the sample. We'll standardize it using our formula for standardization, actual value minus expected value over standard deviation. We'll do this under the assumption that the null hypothesis is true, just like we did for proportions. Next, we'll find a p-value. That's the probability of getting a z-value that's that weird, or weirder. And we'll try to decide if it is sufficiently small. And then, based on the size of p, we will choose to accept or reject the null hypothesis. So let's look at those steps a little more closely, starting with sampling and study design. Remember that if the sample is biased, x bar, that is the random variable that we get by taking sample means, may not be centered at the population mean. If the population is too small, we can't use this formula for the standard deviation for x bar because our selections are not independent. If n is too small, then we can't say that x bar is distributed normally. That means that when we standardize, we won't get the z distribution. Let's look at 3. We will always assess the p-value based on the way the alternative hypothesis is stated, just like we did for proportions. If the alternative hypothesis is, for example, less than, we'll use a left-handed tail. If it's not equal, we will use both tails. Here's what the picture would look like. We have our hypothesized population mean in the center, our observed mean over to the right, and because the alternative was stated using a greater than, the p-value will be the area of the tail to the right. If the alternative is stated using a less than, we'll compute the p-value by looking at area to the left. If the alternative hypothesis is stated with is not equal to, we'll use the area in both tails to find our p-value. Now, looking again at our example that we've been going back to, what about this situation is unrealistic? Well, honestly, if we knew enough about the population standard deviation, we would probably be able to compute the mean, because the mean is required to do that computation for standard deviation. So in general, if the population mean is unknown, the population standard deviation is unknown as well. Soon we'll look at how to handle this situation. But for now, let's look at our one-sided alternative. Continuing to assume that we know the population standard deviation, do we have sufficient evidence to claim that the population mean is less than $5,000? Well, let's start by stating our hypotheses. The null hypothesis would be that the mean is equal to 5,000. The alternative would be that the mean is less than 5,000. That's coming right out of the statement. We can use a computer, for example, to compute or to run the z-test, as it's called. Notice here it's reporting that we're testing that mu is equal to 5, that's the null hypothesis, versus mu is less than 5, that's the alternative hypothesis. So note here that our units are thousands of dollars. We've talked about what potential data production issues could come up. We've already determined that we can use the normal distribution in this case. We see our sample mean at 3.776, remember that's in thousands, and we see our standardized statistic, negative 3.98. Is that large? Yeah, that's pretty big. It corresponds to a p-value of 0 to 3 decimal places. Is that small? You bet. Can't get much smaller. What's our conclusion? Well, our conclusion is that population mean earnings are less than $5,000. So, are we convinced that the actual population mean is less than 5,000? Well, because the alternative hypothesis was framed using less than, we looked for the left-hand tail to compute the p-value, and we got something really small. In general, if it's less than 0.05, we'll call it small. So yes, we will reject the null hypothesis and say that we do have good evidence that the population mean is less than 5,000. Let's look at how to perform this hypothesis test using our calculators. We'll start by going into the Stat menu, and because we're doing a hypothesis test, we'll go over to Tests. We're performing a z-test, so I'm going to select z-test. The first question my calculator asks is whether I'm going to input data or statistics. If you have raw data that's just a list of numbers, You'll select Data here, and notice that further down you see a place for the list. That's where your data is stored. By default, that should say L1. In this case, though, we're given statistics. I know the sample mean and the population standard deviation, so I'm going to go over and select Stats. Notice the display changes. It asks us for mu0. That's the null mean. For the earnings example, our null mean was $5,000. So I'll enter 5,000. The population standard deviation we're assuming is $6,500. The mean of our sample was $3,776. And the size of our sample was 446. Finally, we're asked for the alternative hypothesis. Is not equal to, is less than, or is greater than. In this case, we're interested in less than. So I'll highlight less than so that it's blinking. I'll push enter to select it. I'll go down to calculate and press enter. Here we get our z-score of -3.98 as we saw before. Our p-value of 3.49 times 10 to the -5th. And our sample mean and sample size, just like we saw before. Let's talk real quick about the notation. If we want to test if the mean of all male shoe sizes could be 11, based on sample of 9 male students with mean 11.222, and we'll assume the population standard deviation is 1.5. For each of these 4 numbers, what notation will we use to signify them? Well, 11 is the what we want to test to see if that is the mean of all male shoe sizes. So that is our proposed mean. That will be the mean for the alternative hypothesis. We use a mu sub 0 or mu naught. 11.222 is the sample mean. We'll denote that with an X bar. 9 is the size of the sample. We'll use N for that. And 1.5 is the population standard deviation. For that we use sigma. So in this situation, what conclusion do we think we'll be able to draw just by looking at the data? Well, the sample mean, is that close to 11? Well, it seems like it is, but how do we determine closeness? It's related to the sample size. Because the sample size is small, that's going to make it harder to reject the null hypothesis. That makes that 11.222 seem awfully close to 11. The standard deviation is not very small relative to the difference between 11 and 11.222. That's going to make it harder to find the true mean because there's more spread in the data. So what do you think the standardized sample mean z would be? Do you think it would be very large? No, I don't think so. So, will the p-value be small? Not at all. So what conclusion do you think we'll be able to draw? We will not reject the null hypothesis, and we will accept that the population might be 11. Now, let's say we want to test, again, if the mean of all male shoe sizes could be 11, based on that sample mean of 11.22 with 9 male students. What do we conclude from the output? And again, this is related to what you saw from our calculators. Notice that we got a z-value of 0.44, which is not terribly big. And we got a p-value, and it's two-tailed because We don't have any reason to suspect ahead of time that it might be bigger than 11 or less than 11. So that two-tailed p-value is actually 0.65. That's not even close to being small enough. So, do we conclude that the population mean might be 11? You bet. We will reject the alternate hypothesis and accept the null hypothesis. Notice that we can get the p-value either from the sample mean, using the distribution for the sample means, or from the z-value, that's the standardized mean of 0.44. Because this was a two-tailed test, notice that the combined area was pretty big. The probability, if we take a sample from a population as we described it, that we get one as weird or weirder than 11.222 would be our p-value. Another way to think of it is in terms of z. It's the area of the tails to the left and to the right of minus z and plus z. Looking at these pictures, you can see why it doesn't matter in which way we frame this discussion. If you just use the means and the distribution for sample means, or if you standardize, the result will be the same. Now, in the same shoe size example, would you expect 11 to be contained in the confidence interval for mu? Well, since 11 was deemed to be plausible, we did not reject the null hypothesis, I would expect that 11 would be in the confidence interval. And in fact, if you look at the output again, you'll see it. The confidence interval goes all the way from 10.2 to 12.2. In the previous example, when we were looking at sample earnings, we got a p-value of 0.000 to 3 decimal places, and we rejected the null hypothesis. Do you think 5,000 would be in that confidence interval? Absolutely not. So let's look at the factors that will lead to us rejecting the null hypothesis. When we reject the null hypothesis, we'll say that our data are statistically significant. If you standardize, here's how z plays a role. If the p-value is small, that means that the absolute value of z was large, which will happen if the difference, x bar minus mu naught, is big. That can also happen if n is big, because that square root of n ends up in the numerator once you simplify this fraction over here on the left. We also make z bigger if we make sigma smaller. So if sigma is small, that will help us reject the null hypothesis. Let's look at sample sizes. If n is really big, we may end up rejecting the null hypothesis, even if the sample mean and the proposed actual mean are very, very close together. Remember that a very small p-value means that we have strong evidence against the null hypothesis. But that doesn't mean that x bar may be very far away from the proposed population mean mu naught. If there's a small n, we might not reject the null hypothesis even though it's false. That's a type 2 error. Remember, a type 1 error is when we reject the null hypothesis even though it's true. That's a false positive. A type 2 error is when we fail to reject the null hypothesis even though it's actually false. That's a false negative. When we reject the null hypothesis, either we do it correctly or we made a type 1 error. If we do not reject the null hypothesis, either we did it correctly or we made a type 2 error. Let's say that we are performing a medical test to check if a patient is HIV positive. What's the null hypothesis? What are the implications of a type 1 error? What are the implications of a type 2 error? Which one would you be more worried about? Well, remember, the null hypothesis is always that the status quo holds. There's nothing interesting going on. For this situation, that means the patient does not have the disease. A false positive, then, would be to tell a healthy person that they're HIV positive. A type 2 error would be a false negative, that we conclude that someone who is HIV positive does not have the virus. It's that second one that's more worrisome. Let's look at a legal context. Let's say that someone is on trial for a crime. What's the null hypothesis? What does a type 1 error imply? What does a type 2 error imply? Which one would you be more worried about? Well, in the U.S. legal system, the presumption is that a defendant is innocent until proven guilty. That's assuming the null hypothesis. A type 1 error would be a false positive. That is, that innocent person is guilty. A type 2 error would be a false negative. That is, that we acquit someone who's actually guilty. The first type of error in this case is more worrisome. So remember, when we're looking at sample means are a random variable. They're centered at mu, the population mean. The standard deviation is the population standard deviation sigma divided by the square root of the sample size. And as long as n is big enough, the shape is approximately normal. If we know the population standard deviation, x bar follows the z distribution, or the normal distribution. If the standard deviation of the population is unknown, and n is large enough, like 20 or 30, then our sample standard deviation is going to be very close to the population standard deviation. And so the standardized statistic will be approximately z. So if we know the population standard deviation, or if n is big, we can use z. But what about the other case? If the population standard deviation is unknown and the sample size is small, we'll call this standardized statistic t. Notice what's going on here in the denominator in the computation for t. Instead of sigma, we've got s. That's the sample standard deviation. Like z, t is centered at 0 because the mean of the standard of the sample means is mu. Like z, t is distributed symmetrically as long as the sample means are normal. In general, t will have more spread than z. The tails will be fatter. That's because s, the sample standard deviation, tends to be bigger than the population standard deviation. We will say that t has n-1 degrees of freedom. In general, the shape of the t distribution depends not only on the standard deviation of the sample, but also on the sample size. The smaller the sample is, the fatter the tails. Using these degrees of freedom will allow us to choose which t distribution is appropriate. So remember, if the population standard deviation is known, When we standardize the sample mean, we'll get z. If the population standard deviation is unknown, when we standardize, we get t. And remember, the t's are distributed with a fatter tail. Here's an example. When n equals 7, we would say that t has 6 degrees of freedom. Here are the distributions. You see the z distribution is the tall one with smaller tails, and the t distribution has a shorter peak but fatter tails. If we look at the probability that t is greater than 2 versus the probability that z is greater than 2, how do they compare? Well, you can see it in the tails. The probability that t is greater than 2 looks like it ought to be about twice as big as the probability that z is greater than 2. In fact, the probability that t is greater than 2 is about 0.05, while the probability that z is greater than 2 is about 0.025. We also talked about hypothesis tests. We looked at the z-test for population mean and the 4 steps involved. We looked at examples that involved both one-sided and two-sided alternatives. We looked at the relationship between the hypothesis test and the confidence interval. We considered several factors in rejecting the null hypothesis. If the sample mean is far from the proposed population mean, that will encourage us to reject the null hypothesis. Also, if the sample size is really big, or if the standard deviation is small, that will also help us reject the null hypothesis. Finally, we also looked at the relationship between z and t. Those are the two distributions that we might look at for the way sample means are distributed. We talked about when the population standard deviation is known, we'll get z, but if the population standard deviation is unknown, we'll use t. Though if the sample size is big, remember there's not a whole lot of difference between the two. Comparing the distributions, remember that t has a fatter tail and a shorter peak. As the number of degrees of freedom goes up, that is, as the sample size goes up, the tails of t shrink, and the distribution approaches the normal z distribution.